Well, good afternoon, everyone. Welcome back. I just had quite a good question from one of you about yesterday, saying that really I provided some confusion when I mentioned Foucault's pendulum at the Observatoire de Paris. That was a gratuitous story just thrown in to add a little bit of color to the observatory. It wasn't relevant to the entire discussion of the determination of the distance to the sun or the discovery of hydrogen fusion and the power of the stars. So although I showed you Newton's law of gravity yesterday, Newton's law of gravity was not important to the discussion yesterday. It's fundamental to the discussion today. So I hope I didn't confuse too many of you by just telling the little tiny note that Foucault did his first experiment with the pendulum at the Observatoire de Paris. His main experiment was moved over to the Pantheon in Paris. And those of you who've been to the Pantheon, there's still a big Foucault pendulum swinging there. Today, I want to look at the question, how much stuff is out there? And in particular, I want you to go away today with some understanding of how we know that. You may not go away with complete understanding of how we know that, and we'll blame that on my teaching rather than your comprehension. But we're going to look at how do we know what the mass of things is? How do we know the mass of the Earth, the mass of the sun, the mass of the galaxy? How do we know, or at least think we know, the universe is dominated by some mysterious dark matter and even more mysterious dark energy? And so our story begins in the early part of yesterday's lecture. We're going back to it, to Nicholas Copernicus's then follower, Johannes Kepler. Kepler discovered his three laws of motion using the observations of Tycho Brahe. And I told you how strange Tycho was yesterday. Kepler spent his nearly 20 years studying Tycho's observations, particularly the difficult planet Mars. His first book was called The New Astronomy, and it was the new astronomy. Absolutely revolutionized astronomy for commentaries on the motion of Mars, and that gave his first two laws. It took him, as you can see, another decade to discover his third law, and I hope you're going to think when you see his first law that it's very simple, even though it's an equation. It's a very simple equation. Why did it take him 10 years to discover this incredibly simple thing? Do you know, in science, somebody comes along and discovers something and other people look and say, oh, well, of course, it's so obvious. But until somebody sees it, it's not obvious. A fantastic example of that's back in the 1960s, a Japanese geologist said, do you know, if you want to find meteorites that have fallen out of the sky to study the solar system, go look in Antarctica. If there's a rock lying on top of the ice, it fell out of the sky. And everybody said, oh, well, of course, how obvious. But nobody thought of it before him. And most of the meteorites we've got have come from Antarctica. Kepler discovered three laws of the motion of bodies in the sky, and it's from those laws that we determine mass. And so let's learn about Kepler's laws. His first law says that a planet, he was working on the planets orbiting the sun, orbits the sun in a figure called an ellipse, which is just a stretched out circle. In fact, a circle is an ellipse with what we call an eccentricity zero. The sun sits at one focus of the ellipse, there's nothing at the other focus, and the planet orbits around on this figure. Half the long axis we call the semi-major axis. We always use the little letter A for that. And that's the thing we give you when we tell you how far away the Earth is from the sun. That astronomical unit that was discovered with the transits of Venus was half this long axis. The Earth's distance to the sun varies. One of the reasons it took Kepler so long to discover that the planets move on ellipses is that there was a Greek astronomer 600 BC, 2,000 years before Kepler, named Apollonius. And so far as we know, Apollonius is the first person to write down the mathematics of the ellipse. He discovered the mathematical figure, the ellipse. And Apollonius also invented a dogma which said that everything in the sky, because the heavens are perfect, everything must move on a perfect circle. And that stultified astronomy. 2 millennia, we're stuck because we think things have to move on a perfect circle because Apollonius said so, when Apollonius invented the ellipse. And Kepler said, look, if this motion is so simple as an ellipse, Apollonius would have known it. Can't be right. And that's one of the reasons it took him 8 years from when he got Tycho's observations to finally publish that this simple figure is how a planet moves around the sun. So there's Kepler's first law. It's just how two bodies orbiting each other, whether it's a planet around the sun, the moon around the earth, two stars orbiting each other, very common, they all move on Keplerian orbits. Kepler's second law, a little bit more complicated, but we now understand it in terms of the physics. Kepler found that if he plotted the position of the planets and he made a line from the planet to the sun at two different positions, let's say that this is 1 month of travel of the planet, then this area inside here was always the same for 1 month of travel of the planet. So out here the planet moves slowly, it doesn't travel very far, but it's very long distance to the sun. This area equals that area. That was his law. What we now know is happening is because of the gravity of the sun, as the planet falls closer to the sun, it speeds up. And as it goes farther away, the gravity of the sun slows it down. And in fact, this is a statement of a simple physical law we call conservation of angular momentum, conservation of spin. The important law Kepler discovered, and the one that's going to dominate our discussion of mass in the universe, is his third law. 10 years it took him to write down that if you take the period of a planet in years and multiply it times itself, it equals the semi-major axis of the orbit multiplied by itself twice. That's incredibly simple for a law, and yet it took him 10 years. Why? This is from Kepler's publication. He believed in the music of the spheres. Pythagoras, 500 years BC, and his followers looked at the sky and they said, how do the planets and why do the planets move around the sky? Why do they move? Well, the planets were gods and the gods do as they please. But even to the Pythagoreans, it seemed that their gods should obey nice harmonic laws. They believed that the planets, Mercury and Venus, Mars, Jupiter, and Saturn, they didn't know the Earth was a planet, they're standing on it, and the sun and the moon, which also move through the sky, we'll come back to this on Friday, they believed they spun on crystal spheres. And as the crystal spheres spun, they made a humming sound. And the gods could hear that hum, the music of the spheres. And so could humans who were something more than human, like Pythagoras. His followers thought that he was semi-godlike because he was so brilliant. Pythagoras could hear the music of the spheres. Now, he lived into his 90s. I'm now only 70, but I know that Pythagoras was in fact listening to his own tinnitus, not the spinning of the spheres. For those of you who are with me on that problem, this is not the music of the spheres we're listening to in our heads. Kepler so believed in the music of the spheres that he tried for 10 years to get the orbits of the planets to fit into some sort of harmonic behavior. And he was looking, this is his own musical notation for the planets. It didn't work. And one of the things that makes him a great scientist, he gave up on what he cherished, the music of the spheres, and he discovered this very important third law. Let's look and see how this works from Newton's point of view, because Newton came along and he calculated how the planet should move. So Newton, let's look at the drawing first. I'll explain in words what the equation means. Here's a big object, like the sun, and a smaller object like Jupiter. They both orbit about a balance point in between them. And that balance point is as simple as a fulcrum and a lever. It's as simple as a teeter-totter in a playground. If you've got a heavy person on one end and a light person on the other, you need that balance point over towards the heavy person. And so it's a simple balance point. It's closer to the big body than the far body. We can easily calculate how far away. And the two of them orbit about. This one goes around like that. This one goes around like this. They both orbit on circles about that point. So what Newton discovered is Kepler had missed out that the mass matters. And this is Newton's form of Kepler's third law. It says that the period squared times itself equals the semi-major axis cubed, and now times some units. This is just the number 4. That's pi, as in 2 pi r for the circumference of a circle. This is the gravitational constant from Newton's gravity law. So this is just a number, but you need to multiply by the sum of the masses of the two objects. That was the important thing that Newton put into this law. We can watch two objects go around each other. We can measure the semi-major axis of the orbit. We know these numbers. We can measure the period, and from that we discover the masses. Almost everything we know about mass in the universe comes from that equation. And so all of the masses of the planets in the solar system, the mass of the sun, the masses of stars, our understanding of them come from this. And that's why I belabored that. Now, we don't have to keep looking at this equation. Just know that's where it all comes from. Here's a diagram just to give you some idea. As the two objects move about that point, they're always opposite each other. This is going to be important to us tomorrow when we talk about exoplanets around other stars, because it's the wobble of the stars being tugged about by the planet that lets us determine the mass of the planet and know we're looking at something that's like the Earth. Let's look at the Earth's orbit. This is a side-on view sketch of the Earth orbiting the sun. It's exaggerated, but the Earth is in an eccentric orbit. It's in an elliptical orbit. It passes closest to the sun on the 3rd of January. We just went by that. And that's called perihelion, and more generally called periapsis, but perihelion for the sun. Why is it so hot here in South Africa in January? Well, it's not because we're closer to the sun. The seasons are widely misunderstood, and that should be obvious too if you think about it, because in January we're closest to the sun, and back where I live in England right now, it's 0 degrees. It's not, the seasons are caused by the tip of the Earth in its orbit, not by its distance from the sun. But this accentuates the seasons, so you might think southern summers are a bit hotter than northern summers in general. And then the Earth at its farthest point from the sun, that's called aphelion, most distant point from the sun. And you can see our distance varies from about 147 to 152 million kilometers as we move about on this elliptical orbit. We can now determine the mass of the sun. We know the semi-major axis of the Earth's orbit. The transits of Venus gave it to us back at the times I told you about yesterday. We know how long it takes the Earth to orbit the sun. That's a year. The Egyptians knew that 6,000 years ago. We know those numbers. We can calculate the mass of the sun plus the mass of the Earth, and the Earth's mass is insignificant. And so when we put those together, we find the mass of the sun 2 followed by 30 zeros, 2 times 10 to the 30 kilograms. How do we know how massive the sun is? There's the answer right there. Newton's form of Kepler's third law, and just look how long it takes the Earth to go away around the sun, and then discover how far away the sun is, and all of a sudden we've got the mass of the sun. We know how much stuff it's made out of too. Here's a picture of the sun as we know it in visible light, and the sun rotates with a period at the equator of 26 days, and up at the poles about 35 days. It's only made of gas. It doesn't rotate as a solid body. In fact, the interior of the sun, as I will tell you in a couple of days, rotates in 27 days, and there are very strong easterly winds blowing at the sun's equator and westerlies up at the poles. We're watching sunspots, magnetic storms on the sun, which are blocking some of the light, passing across the face, but look at them changing. They don't last for long. They're constantly changing, and they produce incredible pyrotechnics and fireworks on the surface of the sun with snapping magnetic fields, flares coming off the surface. We can look at the outer part of the sun, which has a temperature of a couple million degrees, by looking in ultraviolet light, way too short wavelength and high energy for our eyes to see, but our telescopes can see it. And when we look at the sun in ultraviolet, this is what it looks like. And that 2 times 10 to the 30 kilograms of material has got gas boiling with hot rising columns and cool falling columns, magnetic fields that are being stretched and snapped, popped into loops sticking out of the surface. It's obviously sped up. It takes 26 days to rotate, but I never get tired of watching these movies taken with the Solar Dynamics Observatory from space of the solar weather. And that weather affects us directly here on the Earth. We get blasted by flares from the sun, and that produces aurorae. It can shut down power systems. If astronauts are out beyond the Van Allen belts on the way to the moon, they're dead when that happens. We didn't have any protection for them back when they went to the moon. They just took a chance it wouldn't happen for the few days they were out there. If you're thinking that the idea of sending people to Mars might be viable, trip to Mars and back is going to take a minimum of 2 years. And in 2 years, we cannot protect the astronauts. Not from the blasts from the sun and not from cosmic rays coming from space. That's a showstopper right now. We cannot send people to Mars now and bring them back alive because we can't protect them from the high energy particles, some of which come from this sort of blast off the sun. The sun is a little star. It's not a big deal. 2 times 10 to the 30 kilograms we call 1 solar mass. You know, 1's a whole lot nicer number than 2 followed by 30 zeros. Don't you agree? So we change units because we think, oh, if we say 1, then we now understand. That doesn't mean you and I have got a good feeling for how much stuff 2 times 10 to the 30th kilograms is. But these stars, these 2 stars, are in the Large Magellanic Cloud. They've got a very interesting name. Let me just think. They're the Very Large Telescope Flames Tarantula Survey, VFTS 352. Aren't astronomical names romantic? So here's VFTS 352. These are 2 stars that together have 57 times the mass of the sun. They orbit each other in 1 day. They're touching. They're sharing material. They have a temperature of 40,000 degrees. The sun's 6,000 degrees. And these stars are going to live less than 1 million years and then blow themselves to bits. But they may merge into a single star and explode, or they may stay separated and explode twice as 2 separate stars. But in any case, we're either going to end up with 1 or 2 black holes. And I'm going to come back to tell you how we know what the black hole masses are too. So this thing's going soon. Maybe tonight. Maybe 100,000 years. We just have to wait. But sometime soon to an astronomer. Well, here's an artist's diagram showing what 2 stars like that are like orbiting each other. They, by theory, radiate energy by something called gravitational waves. That was proposed by Einstein in 1915 when he invented the general theory of relativity, which is an update, an improvement on the law of gravity that Newton invented. So they should be radiating energy just because they're moving around each other, and these gravitational waves come out in this artist's impression as these spirals you see coming out. And so as the 2 stars lose energy, they eventually spiral together, ultimately to explode as a hypernova, as a gamma ray burst, and send out an incredible burst of gravitational waves. That's been the theory for more than 100 years. Since I was a student, astronomers and physicists have been trying to detect these gravitational waves and prove that they're there and use them. 2 years ago, the success came. You may have seen it in the news, and that was that year's Nobel Prize in Physics. Finally, for the discovery of these gravitational waves and the direct measurement of them. So we have another way to look into the stars and study the universe now that doesn't just come from light. We can use this energy coming out as gravitational waves instead of photons. Here are 2 very bright stars and a whole lot of other stars in the sky. I want you to have some appreciation of what happens when we take a picture of the sky. This is a Hubble Space Telescope picture. These spikes are not real. Stars are entirely spherical. They're purely made of gas. But the telescope that took the picture has a second mirror in it that's held up by 4 arms. And when the light comes by those arms, because it's a wave phenomenon, it's diffracted behind them. And it artificially produces these diffraction spikes. So the star doesn't have spikes on it. Not 5, not 4. That's just an artifact. Can you notice that this star's red and this one's blue? Stars have color. You can see that with your eye. Go out where it's dark and look at the stars. You can see the colors. That comes from their temperatures. The red one's cool by stellar standards. The blue one's hot. So I want you to notice they have colors. That has to do with their temperature. We're already talking about their masses. I also want you to notice that this picture, which is a tiny piece of the sky, is just covered in stars. How do we make sense out of the billions of stars of the Milky Way? How do we organize the knowledge that we've gained? with their temperatures, their masses, how far away they are, how big they are. What way can we put that together so that we can kind of hold all the information in one place and begin to learn from it? And this is the answer. This is the most important diagram in astronomy. All right, it's a scientific diagram with lots of information and lots of axes, but let's learn a little bit about it and put it to some use. It's named after Einar Hertzsprung and Henry Norris Russell, a Danish and American astronomer about 100 years ago, who first made this kind of plot. It shows along this axis how hot the star is, from 30,000 down to about 2,000 degrees Celsius or Kelvin. So to me, something that's cool is 2,000 degrees. Something that's hot is 30 or 40,000 degrees. And then along this axis, it shows how bright the stars are. The sun, this is in terms of the sun's brightness. So one solar luminosity is here. The sun has a temperature of 6,000. The sun sits right there in this diagram. Most stars lie along a line we call the main sequence. And this is where stars sit in this diagram for 90% of their lives. This is where they're fusing hydrogen to helium. And since hydrogen's 90% of the atoms in the universe, and the most energy you can get out of nuclear reactions comes from that very first reaction, hydrogen to helium, this is what stars do for most of their lives. It's what the sun's been doing for the last 4.65 billion years, fusing hydrogen to helium. Stars that are very cool and very bright, and these stars up here are 100,000 times brighter than the sun. Cool things don't put out very much light per unit area, and so to be so phenomenally bright and yet cool, they have to be absolutely huge. These are called supergiants, these stars up here, and if you took one of those, put it where the sun is, Mercury, Venus, Earth, Mars, Jupiter, all inside the star. There are stars out there as big as our solar system out to Saturn. That's a late stage in the life of a star. It's something a star does when it gets old. When one of these stars finally dies, it tends to shed its outer atmosphere and leave behind a very dense core. And we're going to look at that dense core. It's called a white dwarf. And then the star appears down here in the diagram where it's very hot, very bright, per unit area, but extremely faint, 10,000 times fainter than the sun. These things are tiny, tiny, tiny. They've got the mass of the sun, but they're only the size of the Earth. They're called white dwarfs. All of that information is embedded in this diagram, and so when we astronomers are talking about stars, this thing comes up first. We just put it down there, and then we start to talk about whatever particular subject is we're interested in. With Newton's form of Kepler's third law, we've learned that these stars down here have got tiny masses. They're only about 1/10 the mass of the sun. Those are the smallest stars that can fuse and make their own light. Whereas these stars up here can get up to masses of over 100 times the mass of the sun. So this is a mass sequence too, and we understand that. The really massive stars squeeze under gravity, and their cores get hot, and they fuse their hydrogen very quickly. And their lives are over 1 million years. These stars down here are very frugal. They're tiny. Most stars in the galaxy are these little stars, and we're going to discover tomorrow most of the planets we're discovering are orbiting about these tiny red stars, and they fuse their hydrogen so slowly, they'll still be fusing hydrogen 1 trillion years from now. The sun's only got a couple of billion years left, and it's had it. So that sequence is a mass sequence as well as a temperature sequence. Let me show you the lives of stars. Stars are born in the galaxy. The Milky Way, 400 billion stars. Between the stars, there's gas, there's dust. We'll see it in the picture. And all the time, gas clouds are collapsing and forming clusters of new stars. Good example, the Pleiades, Subaru in Japanese, Isilimela in Zulu. That cluster of stars was born only 100 million years ago. It's a young cluster to us astronomers. These stars are being born all the time. They live their lives fusing hydrogen to helium and then helium to carbon, and ultimately they grow to be red giants. And so most stars collapse, they form, they fuse hydrogen to helium for the sun for 10 billion years before it's done. And then the sun swells to be a red giant. It will swallow Mercury. It will swallow Venus. It will blow away the Earth's atmosphere and the Earth's oceans. It's going to kill this planet. Sorry, planets have lives just like plants, animals. They don't live forever. And then ultimately the star will go through a series of pulses and blow away its outer atmosphere in something we call a planetary nebula, and down in the core is the little white dwarf, which is the death state of 90% of all stars. But for the really big stars, the massive stars, they're hot. They're bluish, as you saw in the picture of the star. Very, very high temperature stars are blue. Cool temperature stars are red. It's not like in art. In the real universe, the hot things are blue and the cool things are red. That star swells to be a red supergiant and then explodes as a supernova and blasts its material back out into space. This is your great, 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 many times, grandparents. When this galaxy was born, the stars were made of hydrogen and helium. And that's just about all. We can see that. The oldest stars are just hydrogen and helium. But in nuclear reactions in the stars, carbon, nitrogen, oxygen, all the elements up to iron got cooked up. And then in the explosion of these stars, all the elements heavier than iron got cooked up and they were blasted out into space. So when the sun formed 4.65 billion years ago, it's 90% hydrogen, 8% helium, the lightest two gases, and 2% other stuff. And it's that other stuff that makes up the Earth, that makes up you and me, makes life possible. It's all been cooked up in stars since the birth of the universe. Let's look at the white dwarf stars. The most famous example, the first one discovered, is the brightest star in the sky, Sirius, and there's a telescopic image of it. There are those artificial spikes from the arm in the telescope. And with a really big telescope and good resolution, you can see little tiny Sirius B right here. It takes 50.04 years to orbit about Sirius A. We can measure the period of the orbit. We get P for Newton's form of Kepler's third law. We can measure the semi-major axis of the orbit. We get A, and we can calculate the mass. Sirius A has a mass of 3 times the mass of the Sun. Sirius B, this little faint thing, has a mass of 1 times the mass of the Sun. And this man, Subrahmanyan Chandrasekhar, long ago showed us the maximum mass a white dwarf can have is 1.4 solar masses, just a little bit bigger than the Sun. I want to talk to you about that, but first a story about Chandrasekhar. Chandrasekhar sailed from Madras, India, now called Chennai, in 1929. He was 19 years old. He came by ship, took 3 weeks to get to England, where he was to be a graduate student at Cambridge University. And on the way on the ship, using Einstein's relatively new theory of general relativity, which I have to tell you, even to a mathematician, is not simple, Chandrasekhar calculated the maximum mass one of these collapsed little white dwarfs could have. And he discovered this, only 40% bigger than the Sun. He got to England, where he presented this work at the Royal Astronomical Society at Burlington House in Piccadilly. Those of you who've been to Piccadilly, you might have been to Burlington House. It's the home of the Royal Academy, the Art Academy, but there is also the learned societies, the antiquaries, geology, astronomy. At our apartments in Burlington House, where I still go as a member of that society, Chandrasekhar presented this work. And the greatest astronomer of the time, Sir Arthur Stanley Eddington, we'll meet him again in future lectures, just said, "This is absolute nonsense, you're an idiot." Now, there were overtones of race. Eddington was a white Englishman. Chandrasekhar was Indian. There were overtones of empire. This was still at a time of empire, and England ruled India. There were overtones of age. Eddington was the senior professor at Cambridge. Chandrasekhar's some teenage student from India. There were all these conflicts. Chandrasekhar got the Nobel Prize for that work. It wasn't Eddington's greatest moment. Chandrasekhar was right. It's perfectly clear. What happens? When the star runs out of energy, gravity is always waiting. Gravity just sits there in the universe and it waits for its time. At the moment for the Sun, gravity's trying to make the Sun collapse, but the gas pressure in the Sun's pushing out. And so the Sun's gas pressure resists gravity, but when the Sun runs out of nuclear fuel someday, there won't be the pressure to resist the gravity, and gravity wins. And the Sun collapses until all of the electrons that orbit the atoms are packed to the maximum density that's allowed in the universe. It's called the Pauli exclusion principle. It's what governs chemistry and why we have a periodic table. And so the star essentially becomes a giant atom with the electrons packed to the maximum density the universe allows. That makes a white dwarf. The more massive it is, the smaller it is. And as you can see here, typically has about a half a ton per cubic centimeter density. So this thing at a white dwarf would weigh a couple of tons. Incredibly dense and kept from collapsing by the Pauli exclusion principle, this packing of the electrons. Now, I want to tell you that there is another way to determine mass. We're not going to use this very much, but I at least want to throw it in so you know it, because it works for these white dwarfs. Light is made up of photons, and a photon's energy depends on a constant from Planck's constant. It depends on the speed of light, which is fixed, and it depends on the wavelength of the light. Red light is long wavelength, blue light is short. Now, when I throw this thing up like that, luckily caught it so I didn't break it, gravity slows it down and brings it back because it loses energy climbing against gravity. When the light in this room goes up, it loses energy climbing against gravity. But while this can slow down, the light cannot slow down. The speed is fixed. So how does the light lose energy? The only way the energy can get smaller is if this number right here gets bigger. The light gets stretched, the longer wavelength. We call it a redshift because for the visible light, the longest wavelengths are red. Well, for Sirius B, we can measure that redshift, and we can see that the elements like hydrogen, all the wavelengths have been stretched. And from that, we can determine the mass. It's another way to get mass. It's not the main way. Now, there's Jocelyn Bell Burnell. In 1967, I walked into my astrophysics class as an undergraduate at the University in San Diego, and my fellow students said, "Have you heard? They've discovered a star that's spinning on its axis in 1.37 seconds. And I said, "Well, that's absurd. A star can't spin in 1.37 seconds. It would fly apart." He said, "Well, the star is very tiny. It's a thing called a neutron star. They had been theoretically predicted in the 1930s. Jocelyn had discovered pulsars. She was a PhD student at Cambridge University. She and I are in the same 200-year-old dining club in London, so I dine with her in London. She doesn't always come, but we dine once a month outside of summer. And I've also sat on panels with her. And she's a wonderful woman. She's a brilliant scientist. But with her work in 1967 as a graduate student, her supervisor, Tony Hewish, published the theory the next year, and the Nobel Prize Committee gave him the Nobel Prize. Not Jocelyn. It's been a 50-year scandal. Why didn't they give it to Jocelyn? Well, she says, "Well, it's okay. I was a student." She was also a woman, and we strongly suspect that's why the Nobel Prize Committee didn't give her the Nobel Prize. Well, there's an entrepreneur in California. His name's Yuri Milner. Yuri was an early investor in Facebook and Google. Smart guy, at least for money. And he has got so much money in his pocket, and he loves science. You're going to hear more about what he's doing tomorrow. But he funded a set of prizes he calls the Breakthrough Prizes. He hopes that one day, there's a Breakthrough Prize there, one day his prizes will be as prestigious as the Nobel Prizes, but his prizes are worth more money. Nobel Prize is worth $1 million split amongst the 3 people who get it. Yuri Milner's prizes, he gives $3 million to every person who gets it. And he gave a special prize to Jocelyn just last September for her work 50 years earlier. What did Jocelyn do with that money? What would you do if somebody gave you $3 million? Jocelyn's a Quaker. She gave it away. She donated all $3 million to the Institute of Physics for bursaries for previously disadvantaged students, particularly women, but also others. So she's 75, she's got a professorship, she didn't need the money, she's happy to have the prestige, but not really that worried about it. She's had a fantastic career, and she's passed the money on. Well, here's a diagram that's both a picture and an illustration of a pulsar, which is what Jocelyn discovered all those 50 years ago. This is the Crab Nebula. It's the remnant of a star that was seen to explode in the year 1054. It's in Chinese records. Europeans never recorded it, even though it was visible during the day. Why not? In the year 1054, in Europe, it was dogma that the heavens were perfect. And if something in the sky changed, it must be in the atmosphere. It can't be in the heavens, because the heavens are perfect. Europeans didn't even write down that they saw it. It's can be seen in Aboriginal rock art in North America. Chinese have very good records. We know exactly where it was and when it was. And we can measure the expansion of this nebula from the explosion, and if we reverse the expansion, we can actually calculate when it happened. It happened in 1054. It all holds together. Well, a pulsar was discovered right in the center of that nebula. It's spinning 30 times per second. This is a star. It's got twice the mass of the sun, and it's spinning 30 times per second. Material is being shot out of the star and spun up, and so it's like a lighthouse. It blinks every time it spins. It goes blink, 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 but 30 times per second. Obviously, I can't do that. And we can measure that spin. And that's what the artists have drawn here, these lighthouse beams coming out. Interestingly, here at the University of Cape Town, decades ago, the professor then, Brian Warner, and a professor in Texas named Edward Nather used this pulsar to make the most precise measurement of the speed of light that had ever been done, and they got a prize called the Franklin Prize out of that when Brian was here when he was professor. He's still here as professor emeritus. These neutron stars are fabulous. The fastest one spins 700 times per second. They have a mass twice the mass of the sun, and they're about the size of the Cape Flats, 20 kilometers across. Density, 1 billion tons per cubic centimeter. This thing would weigh a couple billion tons on a neutron star. What's happened? The star has exploded. Its core, which is several solar masses, has collapsed. And it squeezed the electrons so much that the electrons pushing out can't resist the gravity. But the universe says you can't pack the electrons any more closely. That's not allowed. But the electrons can't resist the gravity. The universe has a way out. The electrons are pushed into the protons, which are positively charged. They all turn into neutrons, which have no charge at all, and then the neutrons collapse until they're as tightly packed as a nucleus, and then they can't be packed any more tightly. And so the entire star is made out of neutrons packed to the density of an atomic nucleus. If I dropped this thing on a neutron star, it would get accelerated to such speed that when it hit the surface, it would explode with the power of a hydrogen bomb. There is incredible energy in the gravitational field. And here's a really interesting object called Cygnus SS433. That's Sanduliak and Sanders, I think, were the two astronomers who did this. It's just in their catalog. It's a neutron star with a red giant that's swelling up and materials falling towards the neutron star, ending up going around it in a disk, and then that material spins down to the neutron star, and two jets get shot out at 26% the speed of light. The escape velocity from the surface of a neutron star is half the speed of light. Well, what happens if the mass that collapses is just too great? For the most massive stars, neutron stars can only have about 3 or 4 times the mass of the sun, similar to the Chandrasekhar limit. When a massive star collapses, its core can have 10 solar masses. That stuff comes crashing down under gravity. Gravity's just waiting. And even the neutrons can't resist, but they also can't be packed any more tightly. Well, essentially, instantaneously, the thing is squeezed to where the speed to escape is greater than the speed of light, and now nothing can get out. It becomes a black hole. Is there a new law in the universe that gets out of the problem of packing the neutrons more tightly than they're allowed to be packed? If there is, it happens inside the black hole. We do not know what happens inside the black hole. We cannot know what happens in the black hole. We will never know what happens in the black hole.
What is the black hole made of? Is it totally iron? Is it only the iron core that's left?
Okay, what is the black hole made of? Is it totally made out of the iron core? The answer is, when the core of the star collapses, the star has built up to the point that the core is mostly iron. And that goes in, but lots of other material falls in too, including hydrogen and helium. And once things are in the black hole, there's a theorem that says a black hole has no hair. Once something's in the black hole, it's just mass. And if we made a black hole out of 10 times the mass of the sun's worth of U, it would look exactly the same as if it were made of iron or hydrogen. And we can't ever know what the inside of a black hole looks like. No information can get out. Light can't get out. And if you don't like that, if you really don't like the idea that there's a part of the universe that we not only don't know, but we can't ever know, and you insist you must know, stop listening to me. I'm a scientist. Go see a priest. Somebody else is going to have to give you that answer. We scientists can't do that. Here's our first and best case of a stellar-sized black hole. We've got lots of these. There's the actual object right there in that little red box. Not very bright. Here's an artist's impression. It's a blue main sequence star, one of these massive stars burning hydrogen, orbiting about a 15 solar mass thing, and we can't see the 15 solar mass thing. It's invisible. Well, Chandrasekhar showed us that it can't be a white dwarf. They only get to 1.4 times the mass of the sun. An extension of his theory tells us it can't be a neutron star. They can only be about 3 or 4 times the mass of the sun. We got something with 15 times the mass of the sun, and it's invisible. Material from the big blue star is falling down and forming a disk around the black hole, swirling down in, and before it falls in, the gravity releases incredible energy and heats the gas, and the heat from that happening shoots 2 jets out before the material falls in the black hole, and these jets come out at a very large fraction of the speed of light. As the material slams into the disk, it has so much energy when it comes to a stop, it produces X-rays, and this thing flickers all the time with incredibly bright X-ray emission. And so we understand that's a 15 solar mass black hole orbiting a star. We've got a lot of objects like that. Well, let's look out into the Milky Way. There's the Milky Way as seen from Botswana. This is our own southern hemisphere, local Milky Way view on a dark night in a good place. What are you looking at when you look out into the Milky Way? Well, here's another galaxy like the Milky Way with some 400 billion stars, and the sun's orbiting about 25,000 light years from the center of our galaxy. And when we look along the plane of the galaxy towards the center for our galaxy, that's Sagittarius, we see the band of the Milky Way. The Milky Light stars by their billions. The dark bands are dust. They're gas clouds out there. And that Milky Way has got something happening in the center. We can't see right to the center in visible light because the dust, this is carbon soot, water ice, little grains of material. It blocks our view. But if we use infrared light, and we've got infrared telescopes, we can see through it. And we've been doing that for decades. So I'm about to show you a movie. It's a computer animation, but it's based on the data we have for stars right in the center of the Milky Way, 25,000 light years away, orbiting about a thing at the center of the Milky Way. The thing is tiny, and the stars move really fast. We can just apply Newton's form of Kepler's third law. That equation, we can figure out how much stuff is there. This comes from the European Southern Observatory, from the very large telescope in Chile. I go to Chile and observe with this telescope. The artist is throwing in a star being torn apart by the tides into a gas cloud, which the thing at the middle can swallow and grow. Here are the years passing by. We're going to go off into the future. But if you notice, when the stars get near the middle, they whiz around and go back out. They're moving on elliptical orbits, Kepler's first law. They're going through perihelion, Kepler's second law. They speed up. And from the third law, we've determined the mass of the thing in the middle. It is 4 million times the mass of the sun, and it's smaller than the solar system. It's a supergiant black hole. Almost all galaxies have them. So we look into the heart of the Milky Way. It's called Sagittarius A star is the way this is pronounced. And by applying this equation to those star orbits you just saw, we have found a 4 million solar mass black hole around the center of the galaxy. That's small fry, folks. Here's a galaxy called M87, Messier 87. The French astronomer Charles Messier a couple centuries ago just cataloged little fuzzy things in the sky, and this was one of his objects. And in Messier 87, there's a jet coming out from the middle. Here it is right here. In visible light, it's 5,000 light years long. Using a radio telescope, it's 100,000 light years long, and it's moving out at 92% the speed of light. Here's an artist's impression of what's happening in the center of M87. There is a black hole down there with 3 billion times the mass of the sun. Where did it come from? Some star exploded and became a 15 solar mass black hole. Other stars passed close, and the tide from the black hole pulled gas out, and the gas swirled into the black hole. Black holes are really simple creatures. The more they eat, the bigger they get. The bigger it gets, the more it can eat. And that thing at the middle of the galaxy has just eaten up most of the stuff down there until it's grown to have a mass of 3 billion solar masses. And as new stuff swirls in, before it falls in, it can be heated to the point that these jets shoot out at over 90% the speed of light. Here's an extreme case in the constellation Hercules. This galaxy has a mass about 1,000 times the mass of the Milky Way. Multiple galaxies have merged. Its black hole at the center is 4 billion solar masses, and these jets, taken with a radio telescope, so they're artificially colored, stretch over about 1 million light years of space. As that black hole at the middle blasts this material out, we know its mass from Newton's form of Kepler's third law. Now, I want to look at the outer edges of the Milky Way. And so here's another plot, which plots how fast stars orbit the Milky Way, starting from the center and working our way out. The sun is out here. This number is not a number I've given you. It's called a kiloparsec. This is about 25,000 light years. Our sun orbits the galaxy at 220 kilometers per second. You're not feeling that, but right now the sun's going around the center of the galaxy at 220 kilometers per second. It orbits the galaxy. It's orbited the galaxy about 20 times in the lifetime of the universe. The stars orbit at different speeds as you go out because of the mass distribution, but when you get to the outer reach of the galaxy where the final stars are, this is a big surprise. We expect the velocities to drop off. Here's a schematic. We think that once you get past all the stars, if all the mass is in the interior part of the galaxy, the velocity should drop like this according to Kepler's laws. There's the equation. The velocity drops as 1 over the square root of the distance. That's what happens in the solar system. Mars orbits more slowly than the Earth does. Jupiter orbits more slowly than Mars. Saturn orbits more slowly than Jupiter. We understand it. But the galaxy doesn't do that. The stars keep going at this high speed, farther and farther and farther out. If the law of gravity's right, then there's an awful lot of stuff there that we can't see. And we call that dark matter. I'll tell you in a little while why it can't be made out of stuff like you and me. Oh, this picture's phenomenal. This is a Hubble Space Telescope picture. It's a picture of a tiny piece of the sky, tiny fraction of the size of the moon. And these elliptical galaxies are galaxies that have grown by eating spiral galaxies like ours in mergers. They've grown to trillions of solar masses. And look at them all over the picture. This is a cluster of galaxies. Well, you've seen the Pleiades. Stars orbit each other in clusters. The universe is expanding as a whole, but within that overall expansion, there are clusters of galaxies, where galaxies by their tens of thousands all orbit about each other. And that's what's happening here. There's a star. You can see the spikes. You might find a couple of others in here, but virtually everything you see in this picture is a galaxy of 400 billion or a trillion stars. It's really hard to get your mind around these numbers. The mass of those galaxies is producing gravity, and gravity affects light. Einstein predicted that with general relativity. Eddington actually showed it for the first time with an eclipse in 1919, where he showed that as light passed by the sun during an eclipse, the stars moved because light falls down in a gravitational field. That's happening in this picture. Behind all these galaxies, much further away in the universe, much further back in time, there's another cluster of galaxies, and the gravity of this cluster is twisting and distorting the light. It's acting as a lens, but a gravitational lens. And these streaks you see here, can you see the arc of blue, this arc here? Those are galaxies that have been distorted by the power of the gravitational field. And that tells us that most of the mass that's there is not in those galaxies. It's in something we call dark matter. Here's the most extreme and best case for dark matter. It's called the bullet cluster. And in the bullet cluster, 2 clusters of galaxies, one cluster moving this way and another one moving this way, have passed through each other. And as they pass through each other, the gases rammed together and been heated to millions of degrees. And the purple is from an X-ray satellite showing the X-ray emission from this intensely hot gas. So the galaxies clusters ran together, the gas slammed into each other, the gas came to a stop and got heated to 15 million degrees, but the blue over here shows the distribution of mass. The dark matter kept going. This is considered to be the best case for the reality of dark matter in the universe, this so-called bullet cluster. Now, another diagram for the universe as a whole. We need 2 of these, and then I'll get to the punchline for the universe. This plots the mass fraction for various elements in the universe, and this is the current density of the universe. This vertical band is the density of the universe. It's 5 times 10 to the minus 30 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. The universe is pretty low density, good vacuum to us. There's how much stuff there is in the universe. This is the fraction of helium-4, that's the normal part of helium, compared to hydrogen, on the order of 1/10. This is the amount in the universe of helium-3, light helium. This is heavy hydrogen, and this is the next element, lithium. The black lines are our predictions. The horizontal bars are the observations. They fit together beautifully. We calculate how much hydrogen and helium should have come out of the Big Bang, and it works. But it only works if the mass of the universe is 5% made out of stuff like you and me and the sun and the black holes and the moons and the stars. So the universe can only have 5% mass made out of stuff like us. The rest of it has to be this strange material. This problem has gotten more complicated only a little more than 10 years ago. This is basically reaching out into the universe back in the past. This is the shifting of the light due to the stretching of the universe. This is now, and that's looking back into the past. This is a measure of how far away galaxies are, and we measure the distance with these supernova explosions. And the Nobel Prize was given for this plot, where just a couple of dozen galaxies were shown to lie above this line for either a universe that was stable or would someday collapse. This plot indicated that the universe with time is accelerating, going faster. What makes it go faster? Einstein's greatest blunder, he said so himself. It's called the cosmological constant. We use the Greek letter lambda for it. So the lambda, cold, dark matter model of the universe is our best model. It's made out of 5% stuff like you and me and the stars. It's made out of 26% dark matter, and we don't know what that is. And it's made out of 69% dark energy, and we know even less about that. And so I would like you to understand that we think the universe is infinite. We can only see an infinitesimal piece of it. And of that infinitesimal piece, we can only observe 5%. And so from 5% of an infinitesimal piece of an infinite thing, we have correctly concluded the model for the whole thing. And I would say maybe it's our best model, but keep your wits about you, folks. This may change. Look on a large scale. This is just in the vicinity of our sun. We have now plotted the positions of galaxies and clusters of galaxies. Sun's at the middle, our Milky Way. And you can see that the galaxies now are not only in clusters, but the clusters cluster, and they form great walls. And there are huge voids between them where there aren't any galaxies. I've got colleagues in my department who work on modeling this kind of thing and predicting from the Big Bang how matter should be distributed in the universe. And their computer models suggest something like this, that the galaxies and clusters of galaxies will lie along filaments with great voids between them. And that is what we see, but of course they're matching observations that have already been made. All of the things I'm telling you about the universe and the mass for the universe assume that the law of gravity from Newton, or Einstein's version of it, is correct. What if the law of gravity is not right? That's a serious question. Serious scientists are looking at that. They've not succeeded in finding a version that fixes the problem, but if there's a different law of gravity, the dark matter and the dark energy go away. We don't need them anymore. On the other hand, there are projects that are looking for dark matter and trying to detect it directly, and if it's found, we would have lots more confidence in that theory. So this was a real science lecture today, folks. There are going to be a lot more pretty pictures and easier going tomorrow. But I wanted you to go away with more understanding of what it means when we say how much stuff is out there. How do we know? And for most of you, you probably can't do the calculation yourself, but you've seen from me today that for me as a scientist, it's just a simple little equation. And we just watch the stars going around each other, and the information just falls out. Thank you for your attention. Thanks for staying awake. Tomorrow will be easier. Questions?
Can I ask you, you showed us the HR diagram, or whatever you called it, and there were colours on that, and you explained a lot from that.
Okay, the question is about the HR diagram and the colors. And we do measure the colors of stars to measure their temperature. It's temperature that we're after. Traditionally, we did that in the optical because that's all we knew how to do. With the infrared and the ultraviolet, for the very hot stars and cool stars, we can do better. But we're still measuring the brightness of the stars at different wavelengths. We've just stopped thinking as humans who can only see in the visible, and we're now